All right, everyone, let's go ahead and get started. Welcome to week 3. You guys had a homework assignment that was due today. I had one question on it, so I think most people were able to follow what I was trying to get at. And so, great. So we're gonna start with some slides. And today, just to give you a high-level overview, we're going to jump into a classification problem. And in particular, it's predicting student loan prepayments. So there's some student loan data that I got, and we're going to be digging into that. And in order to do our classifications, we're going to introduce a couple of new techniques. One is called logistic regression, and another one is a sort of a collection of techniques that are called tree-based techniques. So there's decision trees and random forests, and those are the two main ones that we're going to be focused on. So that is a high-level overview. Let's go ahead and jump into the slides. I'm going to share my screen. Go into files here. Under my folder, we've got the slides. And we're going to grab 3 and 4. Okay, logistic regression. Is there a question? Someone went off mute for a second. No problem. Just wanted to double check. Okay, let's talk a little bit about univariate logistic regression. So logistic regression is a technique for classification. So let's say we have some binary label y, and we're trying to predict it from a single numeric feature. And logistic regression can be extended to labels that have more than 2 outcomes. However, it gets pretty tricky and untractable. The standard use case is for a binary outcome, like prepay or not prepay. So our approach to modeling y given x is that we're going to model the probability that y is positive or equals to 1, has one of its outcomes given the value of x. And this is how logistic regression proceeds. So in particular, we assume the conditional distribution, which is just given by this expression, is given by this function. And I think this should be a big X here. So it's given by this function. So the exponential of beta plus beta 1x over 1 plus the exponential of beta naught plus beta 1x. And that's called the logit function. The logit function or the logistic function. That's what this is referred to. And let me just say, we're not going to get too bogged down in the theoretical or mathematical details of all of this, as per usual. I just wanted to give you guys a little bit of a high-level overview of some of the background math, and mostly we're going to focus on how to implement these things in scikit-learn. So oftentimes it's useful. Well, actually, let me back up and say, in a lot of real world contexts, for example, in gambling, probabilities are stated as odds rather than probabilities. That's typically not what's done in more academic or business type settings. However, using odds is actually a useful way of seeing the structure assumed in logistic regression and comparing it to the structure assumed in simple linear regression or just linear regression. So odds are defined as the probability of some outcome divided by 1 minus the probability of that outcome. So the probability of it happening divided by the probability of it not happening. And when we assume this conditional distribution, we get that the following odds ratios. So this is the odds ratio. The probability of x divided by 1 minus the probability of x is equal to the exponential of beta naught plus beta 1 times x. And if we take the log of both sides, this is referred to as the log odds, and that equals beta naught plus beta 1 times x. So this drills down into a kind of easy comparison of linear regression or versus logistic regression. So in simple linear regression, beta 1 gives the average change in y for a 1 unit increase in x. And in univariate logistic regression, a 1 unit increase in x increases the log odds, this quantity, the log odds of y by beta 1. So a nice succinct way of describing it. So let's talk a little bit about maximum likelihood. So let's say we've got some training data that's going to be used to fit our logistic regression. If you recall, in simple linear regression, in order to do our fitting, to fit our line or our plane, we used least squares, i.e. the minimization of the residual sum of squares as our criteria for choosing our beta hat 1, the slope of our line. In logistic regression, we'll instead maximize the likelihood function, which is defined as this expression. We're going to choose the xi that maximizes this. And least squares is actually a special case of maximum likelihood. This is a little note to myself to flesh this out further. So in simple linear regression, we are minimizing residual sum of squares. In logistic regression, we are maximizing the likelihood function. Don't worry about this too much. It is worth noting that qualitative predictors can be added, but you'd have to do a dummy variable approach. Okay, let's talk a little bit about multiple logistic regression. I'm just going to make a few comments about this. I will say that the derivations for both logistic regression and multiple logistic regression are pretty hairy. I wasn't able to find one that I thought was particularly useful or coherent. So these are just very high level remarks. So now we're trying to predict the probability of a binary y using multiple features x1 through xp. And in order to do this, we're going to model the conditional probability that y is positive or y equals 1 given x. And we're going to assume that this probability is this expression. So now instead of having just beta 1 times x, we've got a linear combination of our x1 through xp. And that leads to the log odds of x being just this linear combination plus a constant term. So that's really it. I don't want to say too much more. Let me see. Do I have any other comments? No. So that's all I really wanted to say about linear regression. I'm sorry, logistic regression. And let's jump into tree-based methods. Let's just reiterate some of our notation. So we've got we're considering some kind of learning problem. We've got a training data set that consists of n different observations of p features. So the ith observation of the training data is going to be this vector, xi1 through xip, and I ranges from 1 to n. And then yi is going to denote the label observed, I'm sorry, the label observation associated with this particular, the ith feature observation. I think when I wrote these slides, it was before I had written the introductory remarks slides, which basically goes over all this stuff in greater detail, but we'll just go through it just for a refresher. Okay, we are trying to construct a prediction function f based on our training data, such that for feature observations that are not in our training data, it produces a reasonable prediction. And once the actual label is realized, we can compare it to our prediction. And if we repeat this for many out-of-sample observations, we'll get a sense of the overall performance of the prediction function. So that was just some background. Now let's talk a little bit about decision tree regression. And the first thing I want to talk about is regression via partition, which is a more general concept. So let's consider a regression problem where we're making predictions based on p quantitative features. So they're all numeric features. So this means that the space of all possible feature observations is in p-dimensional Euclidean space. And let's let R1 through Rm be some partition of p-dimensional Euclidean space. And I'm not saying anything about what the nature of R1 through Rm are like. It's just some partition. Later, when we talk about decision trees, we will make some stronger assumptions of what the nature of R1 through Rm are. So, but for right now, we just have some partition. So let's let y hat rj be the average of all the training labels whose associated training features lie in rj. So for each rj, we can average all the labels that are associated with features in here. And that's what y hat rj is. So if we build a regression based on this partition, it's a very simple looking prediction function. So we take some out of sample feature observation, and let's say it happens to be an RK, which is one of the elements of our partition. Then the prediction function of this feature observation is just going to be this y hat, the average of all the labels that are associated with RK. Very simple, very intuitive. Our prediction function is just averaging over the partition elements effectively. So for some fixed partition size, we'd like to find a partition R1 through Rm. So, oh yeah, so to back up, okay, so that's given a partition, how do you build a regression off of it? Very simple recipe. So now the harder question is, how do you actually create a partition in a useful, meaningful, optimal sort of way? So if we fix a partition size M, we're going to say 10 or 100 or 1,000 or 1,000,000 or whatever. We'd like to find the partition such that the residual sum of squares is minimized. Same concept as in linear regression, minimizing residual sum of squares. But to do this arbitrarily for a given m is computationally infeasible. It would take forever to actually compute. So a decision tree is one approach to constructing a meaningful and possibly effective partition of p-dimensional Euclidean space in a way that is also computationally feasible. And here's how the decision tree partitioning algorithm works. So we have p different features, right? So we can think about p as being the p different dimensions of our feature space. And let's let j range anywhere between 1 and p. And let's let s be some number. So we're going to use this s to essentially divide all of Euclidean space along this jth dimension. And so for a given j and a given s, we can create these two half planes, if you will, but it's a, they're not even planes, they're half spaces. But of course, in dimensions bigger than 3, it's hard to visualize them. So these are two, we're breaking the Euclidean space into two half spaces. And we're going to do it as follows. So R1 is the set of all vectors such that the jth coordinate is less than s. And R2 is the set of all vectors such that the jth coordinate is greater than or equal to s. And based on this, we'd like to find the j and the s such that the total residual sum of squares is minimized. So if we basically break our space into two parts and then have a very coarse partition-based regression off of that, which j and which s will produce the minimal residual sum of squares. And it turns out that if you have not too many features, this can actually be done fairly quickly from a computational standpoint. So that's basically what one step of the decision tree partitioning algorithm is. And it's basically a repeated process, so we'll talk about it. So in our previous step, in the previous slide, what resulted was a two-region partition of the feature space RP. Let's just call them R11 and R12, where this superscript refers to the step that we're on, okay? So next we want to split one of these two such that and then look at a regression based on the three region partition such that the total residual sum of squares is minimized. And that's pretty easy, right? You can do it for this space and then do it for this space, compare the residual sum of squares, whichever one is lower, go with that partition. So once we've done that, we're going to end up with a three-region partition of the feature space. Call it R21, R22, R23. And now the superscript 2 is denoting the fact that we are on the second iteration of this algorithm. And also note that one of the R2i's is identical to one of these. because we're only splitting one of them. So one of them is going to remain intact. So a decision tree partition is constructed by repeating this process until some kind of stopping criteria is met. And some examples of that are the maximum number of iterations that are allowed, the minimum number of nodes or feature observations in each region, the maximum number of nodes, the maximum number of leaves, I think it's called. There's all sorts of terminology and I get it all confused, but conceptually, it's kind of easy to understand. And just looking ahead to your assignment, you guys are going to use decision trees and decision trees and random forests to make predictions on these student loan prepayments. And one of the things you're going to do is tweak hyperparameters that are effectively going to be things like this: number of iterations, minimum number of nodes, et cetera, that are going to affect the variance and bias of the various models. And you're going to tweak them to get them as optimal as you think you can. But you'll see a lot more details on that in the tutorials that we work through. Okay, that was decision tree regression. Now let's talk about decision tree classification. So we have a classification problem, and we're trying to make predictions based on P quantitative features. This means that the space of all possible features is, again, p-dimensional Euclidean space, and we have some partition. Again, this is the setup that's very similar to the regression. So here's where we're differ. We're going to let G hat R be the most common of all the training labels whose associated training feature instances are in RJ. So G hat RJ is the most frequent, or the highest, the training label that has the highest probability in RJ. And what it means to have a classification based on this partition is to say that our prediction function F is simply, you take a look at the feature observation you're trying to predict on, you look at which partition it's in, and then let's say it's in RK, then your guess or your prediction is just simply going to be this G hat of RK, whatever is the most prevalent class in that partition. So the algorithm for constructing a classification decision tree is very similar to that of regression, but we can't use residual sum of squares minimization as our criteria at each iteration. So then if we have some partition, the total misclassification rate for this partition would be this expression. And that makes sense. So our guess is always going to be the one that has the highest highest probability. And the probability of misclassifying then is 1 minus that probability. And then we have to do a weighted average of that based on the size of each of the partitions, which is what this is. But so one thing we could think about is, well, do we just want to minimize the misclassification rate? And intuitively that makes sense, but from a computational standpoint, it turns out to be not quite sensitive enough to be useful for this partition construction. So we use a couple of different other measures of misclassification. And they are the Gini index and cross entropy. Two measures of partition impurity that are typically used when we construct classification trees are, as I said, Gini index and cross entropy, and they are defined as follows. You basically sum over all the partitions and you sum the probability times 1 minus the probability. P hat MK. Just 1 second. Anyway, I'm not going to worry about it too much. Pretty sure these expressions are right, but they're never going to come up in this class other than this. And then cross entropy is this expression. The punchline for these is that both these measures are small when the probabilities are close to 0 or 1, which would mean that there's a high degree of partition purity, which is to say that our partitions consists largely of one class label. And in essence, this is good because although you're not averaging, you're doing something like averaging, and there's less averaging going on in each partition, over each partition. And if those partitions are large enough, then you have a very good prediction mechanism. So as it turns out, using either one of these misclassification or partition impurity measures leads to similar kind of trees. You can use both in scikit-learn. The Gini index is a good default to start with, and it is the default in scikit-learn decision trees. All right, that was basic vanilla decision trees. And now let's talk about how they are oftentimes combined or modified to produce better classifiers, or more generally, better learning techniques. So these are generally referred to as ensemble tree-based methods. Decision trees are easy to understand, but they tend to have poor performance. They just don't do very well in actually making predictions. So there are several ways that you can refine them or make them more sophisticated that can improve performance. So one is called bagging, which is short for bootstrap aggregation. And the idea is that you fit many small trees using subsamples of the training data. And then your prediction is the average of the results of all the subtrees. Random forest takes it one step farther, where you fit small trees to random subsets of the features and the training data. So in bagging, you would use all the features, but just use a subset of your training data for your various subtrees. In random forest, you actually use only some of your features in each of the subtrees. And then you again average over the results. And then gradient boosting is sort of an iterative method. And we might get into it a little bit for a later tutorial. I'm trying to see if I can get it to work. The truth is, oftentimes I can't get it to really produce reasonable results. And a lot of that has to do with just tweaking you need reasonable starting hyperparameters, which is a hard thing to kind of figure out straight out of the box. And but I might, I'm going to keep messing around with this tutorial that I have going, and we'll see if we can't get an example. So gradient boosting is where you fit one tree and that produces residuals, and then you fit a tree to its residuals, and then one to the aggregate residuals, and the final model is an aggregate progression of all these fitted trees. And again, don't worry about gradient boosting too much because I don't know if it's actually going to come up in our tutorials, but if it does, we'll flesh out this idea a little bit better. So bagging, specifically, this is where we calculate B different bootstrap prediction functions. Call them F hat 1 through F hat B, and then F hat bag is just the average of those. And this, of course, only makes sense in a regression context. For classification, the averaging can occur by a plurality vote. Like you can just see what the predictions are for each of your subtrees, and then say, well, whichever one's the most prevalent prediction in each of the subtrees, or in the collection of subtrees, is going to be my prediction. Or otherwise, you can take an average of the probabilities. So the way that, an average of the probabilities of the given subtrees, and then so the benefit of this is that if you're extremely confident about a specific classification, then that's going to get a higher weighting. Whereas just a straight plurality vote gives equal weighting to each classification, each subtree classification. For a bagged prediction, each training observation will not be used by some of the bootstrap predictions. So you have sort of built-in holdout sets. So when an observation is not used for training, you can calculate an out-of-bag prediction and its associated error. So you get an out-of-sample cross-validations calculations that are sort of built into the fitting process, which is kind of nice. And you can store and analyze them with scikit-learn. I typically still just use holdout sets and cross-validation for it. I haven't used the out-of-bag stuff, but I'm sure you could, and it would probably reduce some of the runtimes. As you'll see, some of the runtimes can get kind of hairy, and by hairy, I mean long, which isn't a big deal if you leave yourself enough time, but probably using some of this out-of-sample or out-of-bag built-in cross-validation would be beneficial. I might try to throw that into the final exam, one of the final tutorials as well, because I haven't really taken the time to look into that stuff. Okay, let's talk a little bit more about random forests. So, like bagging, we are growing trees based on bootstrapped training data. So randomly selected subsets of our training data. Also, for each subtree, we're only going to randomly select some subset of the features to consider for splitting our space into partitions. And a typical value is a square root of the number of features. And the idea here is kind of cool. So if there's one very predictive feature, then all the bootstrap trees would look very similar. And so their predictions will be highly correlated, and averaging over them is just going to make them less effective. It's going to provide less information. So by randomly selecting, then you can effectively better garner the information that's in some of the less predictive features. And I think ensemble methods have a very intuitive appeal. And I guess I would do this sort of thing a lot even before I knew to call them ensemble methods. If you have various ways at arriving at a prediction or a forecast, and you're not really super confident as to one being better than the other, then why not just average over all of them and diversify that model risk? Okay, so just some random notes. In the process of fitting trees, we can record the amount of goodness of fit improvement associated with cuts along the features. In regression, this is RSS reduction, and in classification, this is Gini reduction. And the more fit improvement that can be attributed to a given feature, the more predictive that feature is. And of course, sklearn is cool because it will save all this when you fit a tree, and you can just analyze that. So you can get a quick ranking of the feature importance of all the features, which is nice. And usually, every time I've done it, it's pretty much lined up exactly with, at least the top few have lined up exactly with what you'd think, and then towards the bottom, it gets a little random. So let's talk briefly about trees versus linear models. So, and a comparison of their functional form. So in a linear model, we have that our prediction is just a linear combination of our predictors. And in a tree-based model, we have that it's a linear combination of indicator functions on the partition, and the CM being the average over the partition. Okay, the pros and cons of trees. So it's sort of easy to explain the fitting process. It can, binary decision making is oftentimes what's used in human decision making process. So there's a lot of these, and I just never found them useful, but you have these binary decision trees, and that's how this stuff is usually explained. I like thinking about it in terms of regression or classification over partitions, and then you're just coming up with some meaningful way of constructing partitions. I never found those decision trees to be particularly useful, but some people do. And that leads to those intuitive graphical displays, which I don't find that intuitive. Another thing is that there's nothing stopping you from handling qualitative predictors easily with this. The caveat being that scikit-learn does not handle qualitative predictors for their decision trees. But in theory, there's nothing really stopping. You don't have to do a dummy variable approach or one-hot encoding or anything like that. What are the cons? They're not very predictive due to overfitting. And that's regular vanilla decision trees. And similarly, there's a high amount of variance. They're not particularly robust. Another thing that people talk about, and I should put that on here, is interpretability. So the nice thing about a linear model is that if you give some feature observation, you can very easily explain how you take that feature observation and then calculate the prediction. It's much harder to do that with decision trees. And so that's an example of having low model interpretability. Okay. So that's everything I had in terms of slides. Are there any questions?
Yeah, real quick. So when
Yes.
you talk about bagging versus random forest versus gradient boosting, do those, so like as you increase your iteration, do they converge to the correct one? Do we know, or do we just assume that it's getting better?
In my experience, I I haven't noticed. I typically notice an improvement between decision trees and random forests. So decision trees are notoriously, in and of themselves, not particularly good. And so you do need some kind of ensemble method to make them better and make them not overfit. So I would say in general, decision trees, you can just sort of make a broad statement that random forests and gradient boosting is better than decision trees. Now, once you start getting into the ensemble methods, I think it's harder to make a clear-cut case. There's tons of hyperparameters that you can tweak and mess around with, and so and it's a little bit mind-boggling, actually, and your head can kind of explode when you think about all the different hyperparameters and how you actually go about tweaking them. So I think it's more about you really have to get into the actual implementation and see what kind of model performance you're getting. And then I think another big thing to keep in mind is what kind of run times that the fitting processes take, because some of these can start taking a very, very long time to run, and then you'll need to do distributed computing and all this stuff. And are you really getting that much better model performance for that? In particular, gradient boosting trees, they often take a long time to run, at least in my experimentation with them, and don't lead to that much better results. So that's kind of a clear win for random forests over decision trees.
Sure, that makes sense. Thanks.
Yeah, good question. Any other questions or thoughts? Okay, let's jump into some tutorials. We'll go. So tutorial 6, student loan part 1. While that's downloading, I will fire up Jupyter Lab. Give you guys a moment to catch up. All right. This tutorial is an introduction to asset-backed securities and student loans to give you just enough information to understand the context of this classification that we're going to be doing. Asset-backed securities are these fixed income instruments that securitize cash flows from various kinds of loans, such as auto loans, credit card balances, student loans, typically mortgage-backed securities and mortgage-related products that securitize real estate mortgage loans are classified differently. So that's something that I always found confusing. ABS refers to things like securitized auto loans, credit card balances, things like that, student loans, and mortgage-backed securities refer to a different class of securitized instruments. But it's the same general concept, but each type of loan has its own nuances to it. So that's why they kind of break them up. So many of the loans that are backing asset-backed securities have fixed payment schedules that fully amortize the loan amount, although that last part isn't necessarily true. So they also give, oh, I just got a warning that my internet connection is not stable. So if I cut out or something, please give me a shout. So a typical feature of any loan that you'll get, for the most part, especially a retail type of loan, is that you have the right to repay larger amounts or the full balance at any point, and there's no penalty. And so that's referred to as prepayment. Now, just to give you some context, a lot of loans on the commercial real estate side, or business loans, or loans for small businesses or general business purposes, will have stipulations that you can't prepay, or if you do prepay, there's going to be a large, there's going to be some sort of large penalty or something like that. So that is a very valuable thing, to be able to prepay at any point. That's valuable to you as the borrower, and it's also a risk to you as the lender. So the rate at which these underlying loans end up prepaying affects the timing of the principal repayments, as well as the amount of total interest that the ABS owner is going to earn over the course of the life of the bond. And that in turn is going to affect the overall investment performance. So when you're dealing in the ABS space, it's really all about predicting prepayment speeds of the underlying loans. So in this tutorial, we're going to make our first attempt at predicting student loan prepayments. And really, we're just going to be familiarizing ourselves with the data, getting some initial model fets with sklearn, and in the next couple of tutorials, we're going to dig in more to the details of those models. Any questions on asset-backed securities generally before we dig into the code? Okay, let's get started. We're going to import Pandas as PD, import NumPy as NP, import sklearn, and we're going to say PD options display max equals 10. Oh, display max rows. All right, let's read in our training data. df train pd.read CSV. Student loan df train. So that's what our data look like. It's a pretty decent sized data set as far as this class is concerned, a little over 1 million rows. And we can take a look at the columns a little more closely using the info method. So let me just walk through a little bit what each of these columns means. So loan ID and deal ID are really just identifiers for the individual loan, so you don't have to worry about that too much. Loan age is the number of months that the loan has existed. Cosign is a binary variable, it can be 0 or 1, and what 1 indicates is that there's a cosigner on the loan. And what that means is that in addition to the borrower, there's someone else who has vouched and said, I will hold myself financially responsible for this loan as well. So if the actual borrower stops paying, the creditor can go after the cosigner to receive payments and kind of get their money back. And so that increases the overall credit worthiness of the loan. Income, pretty straightforward. UPB is the amount of unpaid loan balance. The monthly payment is the size of the monthly payment. The FICO score is a number between, I don't know how low they go. Let's just say 0. I don't know if you can have a 0 credit score, but it's 0 to somewhere in the mid 800s. And that the higher it is, the more credit worthy you are. And there are a few organizations out there who basically track all of your payments, your credit card payments, your phone payments, all that stuff, and amalgamate those into a credit score. The orig balance is the original size of the loan. Months to repay is basically how many more months the loan is going to be existing before you the loan is finished or fully repaid. Repay status, basically that's also a binary variable, and if there's a 1, it means that you have some kind of delinquency status. So your 60 days, 90 days, that has more to do with defaults than prepayments. But I should know that prepayments and defaults are basically lumped together because student loans, these student loans in particular, are backed by the government, and so even if the borrower default, the student defaults on their loans, the ABS investor is going to be made whole by the government, and then the government is going to go after the student. So there are a number of months to a balloon payment. So as I said above, oh, is there a question? As I said above, most of these loans fully amortize, meaning if you just keep paying your monthly payment for the life of the loan, by the end of the loan, you're going to have a 0 balance. But sometimes that's not the case, and there's going to be a little bit left over, even at the end of the life of the loan. And typically that final amount is bigger than a single monthly payment, and so that's why you call it a balloon payment, to indicate that it's a big payment. And the paid label is just a label that says it either prepaid or didn't prepay, because this is all training data right here. So we've read in our data into memory, so let's go ahead and organize our features and our labels. So LST features. I'm going to say loan age, cosign, income annual, UPB, monthly payment, FICO, orig balance, months to repay, repay status, months to balloon, and that's all we care about. And then DFX. The data frame that holds all our features is dftrain, and you feed in the list of features we just described above, and we can print that out. Okay. There we go. There are features. And let's also separate out our labels. And let's fit our first model, which is going to be a logistic regression. And again, it is a poor choice of words because it's often used for classification. The one thing I will say is that really what we're modeling is a probability, not a classification. And you just have some criteria of if it's over this probability, then we're going to guess 1. If otherwise, we're going to guess 0. So really it is more of a regression, but it's used for classification. A little bit confusing. As per usual, we'll start by importing the constructor function for our model. sklearn linear model import logistic regression. And let's instantiate our model. Random state equals 0. Model logit fit. We're going to fit our model now. dfx, dfy. And then let's say model. Let's go ahead and check the score. Our fitting is done. We can now check our score, which is going to be accuracy because it's a classification. Model logit score dfx dfy. Well, amazing. Our accuracy is 98%. So a question for you guys to think about is, does that mean that we're good to go? Is our work done? Our logistic regression model is awesome, and we can pat ourselves on the back and just start making our predictions. And towards that end, you can also try the code challenge, which is calculate the probability of prepayment in our data set. And when you do that, you might understand the answer to that question. So I'll give you guys a few minutes to work on that. All right, let's begin with the code challenge and calculate the probability of prepayment in our data set. So dfy is our labels, and it's 0 for no prepayment, 1 for prepayment. So we can simply take the average of this and see that only 1.6% of all the loans in our data set actually prepaid. And this is what's called a highly imbalanced data set, meaning one of the classes is far more likely than the other classes. And typically, classification algorithms only work pretty well if the training data is fairly balanced, and clearly we don't have that. So you can see even if we had a degenerate prediction algorithm of saying we always assume that there's no prepayment, we're going to still be right 98% of the time over that. So that's the reason why this is sort of meaningless. That's why we often have to use metrics other than just accuracy in order to assess the performance of a classification. So in order to be able to do that, let's grab the actual predictions of our model, which we can do with the predict method. Model logit predict dfx. So this will produce an array that has the actual predictions. And so now your code challenge is to calculate the probability of prepayment as predicted by our model. All right, let's give this a shot. So we have model, logit, predict, dfx, mean. Okay, so some predictions, but far fewer. What is that? 5 basis points versus 162 basis points. So clearly we are under predicting. So one goodness of fit metric that's different than accuracy is called precision, which is the percentage of prepayment predictions that were correct. So of the ones that we predicted were prepayments, which percent of those actually prepaid? And we'll see that of these predictions, only 1% of those predictions was actually correct. So let's take a look at this. sklearn, metrics, precision score, model logit, predict, dfx, compare that to the actual labels, dfy. There we go, 1%. So a precision of 1%, which is quite poor. Another metric that's useful is called recall, which is the percentage of actual prepayments that were correctly predicted. I'm sorry. So here, 1.6% of these loans actually prepaid. Of that 1.6%, what percentage of those were accurately predicted? So let's take a look. sklearn, metrics, recall, score, model, logit, predict, dfx, dfy. Okay. Of those that actually prepaid, 33%. 1 second.
We can look at the confusion metrics too, right?
Yeah, I don't know how to do that off the top of my head. Do you know can you direct me if you want to?
Yeah, sure.
So let's see. Right. Okay. So you can drop that in the chat if you want to at some point. We don't have to. We can. So obviously, when we're performing classification, we strive for a model that has both high precision and high recall. So it would be useful to combine these two metrics into a single metric, and the standard one that we use is called the F1 score, which is basically just this. It's 2 times the precision times recall divided by precision plus recall. And it's going to be close to 1 when both are close to 1. Both are close to 100%, and it's going to be close to 0 if either one is close to 0. So let's do this. Precision, sklearn, metrics. Model logit, predict, dfx, dfy, recall, sklearn, metrics, recall, score, model, logit, predict, dfx, dfy, 2 times precision times recall divided by precision plus recall. Okay, so a very low F1 score. And of course, scikit-learn will do this all for us. Boom, there you go. So let's now fit our first decision tree. So again, to recap, we can't just look at prediction in our context because we have a highly imbalanced data set. So F1 score, which combines precision and recall, will be more useful to us. And when we use that, we can see that we have a very low F1 score. So let's now fit a decision tree and see if we can do any better. So we can follow our typical recipe. We import the constructor, instantiate the model, and then fit the data to the model. From sklearn tree, import decision tree classifier, model tree equals decision tree random state equals 0, model tree fit dfx dfy. Okay, cool. Oh no, it's still fitting. All right, so now our decision tree is fit. So now your code challenge is to calculate the accuracy and F1 score for our decision tree model and see if we're good to go, if we can just pat ourselves on the back and call it quits. Okay, let's give this a shot. So if we do model tree dot predict dfx, that gives us our predictions. And then we could do, well, we can do model tree score dfx dfy. Then we could do, just make sure that runs. Oh, great. 100% accuracy. Feeling good. Let's do model tree predict, scale learn. What is this? Metrics, that's right. F1 score. GFY. Okay, so great. Accuracy of 100%, F1 score of 100%. So maybe it looks like we can just say we've got a perfect model and call it a night. So unfortunately, that's not the case. And what you're seeing here is the tendency for decision trees to overfit the data, especially if you don't use hyperparameters to constrict them from not running for too long. They're going to typically completely overfit the data. So one way you can check that is do a train test split to see if you take out of sample feature observations, how do they actually, how well do they work in the model? So let's do that now. X train, X test, Y train, Y test equals SK learn, model selection, train test split, dfx, dfy, random state equals 0. Okay, so we'll just call this model holdout equals decision tree classifier random state equals 0, and model holdout fit X train Y train. And now let's check our F1 score on our test set. Metrics, F1 score, model holdout. Oh, still running, sorry. There we go. Holdout, predict, X test, Y test. Okay, so the F1 score on the holdout set is quite a bit lower, 0.36. Oh, and in here we can see the feature importance that are built into the fitting procedure, which is nice. Model tree, feature importances. Okay, but it just spits out this array, which is kind of hard to interpret. So let's actually stick this into a data frame. First, we'll create a dictionary, feature dfx, columns, values, importance, model tree, feature importances, and then PD data frame. And then I want to sort values to make sure that the most important features are at the top. Oh, geez. All sorts of typos. There we go, finally. Okay, so month to balloon payment. That's actually interesting. I wouldn't expect that that would be the most important feature, but that sort of makes sense. If you're getting close to a balloon payment, then you're probably getting pretty close to the end of your loan. And a couple things. One, if it's a default, then and you're just like, I'm not going to be able to pay this loan off, I might as well go ahead and default now. And the other thing is, if you're like, well, this loan is about to become due anyway, so why don't I just pay it off now because I have the money. So yeah. All right, now let's do random forest. So this is going to be the final classifier that we look at for this tutorial. And again, a random forest is gotten by fitting several decision trees to random subsets of the features and then averaging the results. So the hyperparameter n estimator controls a number of sub-decision trees that will be aggregated. So let's go ahead and fit this model from sklearn ensemble import random forest classifier model forest equals random forest. Oh, just going to run this first. Okay, random forest. And estimators equals 10, random state equals 0, and then model forest fit dfx dfy. Yeah, random forest can take a while to run. There we go, finished running. Let's take a look at the Ensample F1 score. sklearn metrics F1 score model forest predict dfx dfy. Okay, so Ensample F1 score of 90 looks pretty good, but probably too good to be true. And let's check our, let's use our holdout set to refit the model. Model holdout forest equals random forest classifier and estimators equals 10 random state equals 0. Model holdout forest fit X train Y train. Okay, so that worked. sklearn metrics. We're going to check the F1 score. X test, Y test is 0.49. Okay, so a bit of an improvement over decision trees on the holdout set. All right, so that completes the first tutorial on student loans. Are there any questions? Okay, let's move on to the next lesson. Student loan part 2. All right, in this tutorial, we're going to talk about an alternative goodness of fit metric and a little bit of cross-validation in this context. Just one moment, guys. Okay, let's import the packages that we need. Import pandas as PD, import numpy as NP, import sklearn PD options.display max rows equals 10. Okay. We'll read in our training data. df train equals pd.read CSV, student loan CSV, and df train. So that's the same training data set as before. We can take a look at the columns, df train, info. Okay, great. So this is just organizing our features and our labels, which we don't need to retype this code. So we can just uncomment it. So we're doing, we're going to use holdout sets later. And since we're doing our data wrangling, let's go ahead and just take care of this now. sklearn model selection, import train test split, x train, x test, y train, y test equals train test split df x df y random state equals 0, test size equals 0.1. Okay, and a little code challenge for you guys to make sure you're still awake is to verify that xtrain and xtrain and xtest are being correctly sized using the test size parameter. All right, let's give this a shot. So we can say xtrain, what is it? It is a data frame. So shape 0 divided by dfx shape 0 is 90, and then test is 10%, which is what we'd expect. Test size was 10%. Okay. So let's review the traditional goodness of fit measures, accuracy, precision, recall, and F1, and we'll do this in the context of linear regression. So from sklearn, linear model, import logistic regression, model logit. I'll do this. Equals logistic regression. Random state equals 0. Solver. So you have to declare the solver or you'll get some kind of weird warning message. So LB FGS model logit fit dfdy. Okay, so that is fit. Let's get our predictions in an array. So, there we go. And let's print accuracy. DFY 3 precision model logit score error predict logit df y, make sure those, oh, dfx, oh, df y, oh geez, what's going on here? What's going on? Oh, that's what's going on. sklearn metrics precision score. Recall. Recall. Okay, and your code challenge is to calculate the F1 score. Okay, this is pretty straightforward. We'll just say F1 score. And these are all in-sample metrics. And so let's actually use a holdout set that we created above to train this model and then test against the test set. Holdout equals logistic regression, random state equals 0, model logit, holdout, fit, x, train, y, train. Great. And then I'm just going to uncomment this. This is just printing out the accuracy, precision, recall, and F1 score for the holdout set. All right, I think this is a good place to take a break, actually. So we're going to do a 20-minute break today. So let's start back up at 7:33. All right, folks, it's 7:33, so let's get back to it. Let me reshare my screen. Okay, so far, all of our goodness of fit measures have focused on tallying the accuracy of individual predictions. But if you're a ABS investor, you don't really care which particular loans prepaid, but rather the total UPB of the loans that repaid, the total loan balance that repaid. So let's calculate the total balance of the loans that prepaid in the data, in our training data. So we'd say DF train UPB paid label we'll create a new column, assign prepay UPB equals lambda DF UPB times DF paid label prepay UPB sum. Okay. So what is that? 63 million or something like that? $683 million. UPB, prepay, actual. I'm going to stick this in a variable. We're going to use it later. UPB, prepay, actual. Okay, so that's the UPB that actually prepaid. Let's see, based on our logistic regression model, what the loan balance prepaid. And so basically it's the same code. We don't need to write it over again, except this time we're using the predictions rather than the actual paid label. And if we calculate that, we see it's a much smaller number, 28 million or so. So let's calculate the ratio, UPB, prepay, logit, UPB, prepay, actual. We only captured about 4% of the total UPB. So under the hood, most classification algorithms calculate a probability for each class. And then the specific prediction is simply the class with the highest probability. So based on this, we're going to come up with a new metric called the expected value of total balance of loan prepayment. Expected UPB, I think is what I call it. And, but first, let's just take a look at what the prediction probabilities are with this predict proba method. So model logit predict proba dfx. So the probability of default is this. So we can just capture that with the following, is the second column. So we can capture that with the following code. We can pull it out with this code, predict proba dfx. And pull out that array. So now let's calculate the expected value of the UPB prepaid based on the predicted probabilities of our logistic regression model. df train assign predict logit equals model logit predict proba df x assign prepay UPB logit lambda df predict logit df UPB. So multiply the prediction probability by the UPB of that loan. Then we can sum that up. Prepay UPB logit sum EV logit. Okay, great. So that looks more in line. Let's take a look at our calculation. EV logit UPB prepay actual. So from an in-sample standpoint, it looks like our expected value of UPB is dead on. But now let's try an out-of-sample measure with our holdout set that we created above. So we'll create a new model with just the training data from our train test split. Logit holdout equals logistic regression random state equals 0 no, let's fit this to the train data. And now let's calculate the prepaid test UPB. Let me just do this first. X test. Let's merge in the Y test labels. Index equals true, right, index equals true. Assign UPB prepay lambda df UPB times df paid label. And then let's say UPB prepay sum. Okay. What do we call this? So in our test set, these are actually what prepaid. This is actually the UPP that prepaid. And then here's how we pull out the out-of-sample predictions for our test set. Model, logit, holdout, predict, proba, x test. Okay, so the code challenge, I made a mistake and I didn't delete this out. So it says calculate the out-of-sample expected value of the prepaid UPB for the holdout set and find its proportion relative to the actual prepayment. So if you feel like being studious, you can delete that and see if you can figure it out yourself. And I'll give you guys a few minutes to work on that. Okay, let's just look over this solution here. So we grab our test set, then we put our prediction probabilities in as a column. Then we multiply the UPB times those prediction probabilities, and then we sum up this column to get our expected value. And we see that we captured about 98% of the UPB in our test set. So this holdout set methodology can be generalized to n-fold cross-validation. The set of goodness of fit measures that result from a cross-validation are, as you know, in aggregate more robust than a single holdout set. So we're going to look at what that code looks like for a decision tree classifier. So from sklearn tree, import decision tree classifier, model tree equals decision tree classifier, random state equals 0. And then we can just use this cross-validate from model selection to give us what we want. So DCT CV equals sklearn model selection cross-validate. Then we stick in the model, which is a model tree, the features, the label, the various scoring methods we want to use, and we can put in a list of them. F1, which is great. We don't have to do one for each one. Precision and recall. So we're doing this for the standard suite of goodness of fit measures. And in the next tutorial, we'll do a cross-validate for our expected UPB metric. So let's let this run. It'll take a little bit of time because it's going to do 5 different decision trees. All right, so now that finished running, and your code challenge is to calculate the average F1 score from this cross-validation scheme. All right, let's give this a shot. DFCV or DCT CV. We can pull out the test F1 and then we can give it an average. Oh, just CV. Average of 0.35. So the goodness of fit metric that's going to be most useful to us is the expected value of prepaid balance. That does not fit neatly into to cross-validate. So we're going to have to write a little bit of boilerplate code. Luckily, sklearn is going to do a lot of the heavy lifting for us to actually come up with the k-fold cross-validation sets, which is kind of the grossest part that yields no real insights. So once that's done, you're going to have enough tools to work on your student loan assignment. And I'm going to send out details of that assignment on Friday. Basically, everyone's going to be assigned different hyperparameters for tuning for a couple of different classification models. And we're going to use two bases for selecting the optimal hyperparameters. A 10-fold cross-validation with expected UPB and a 10-fold cross-validation with F1 score. Any questions before we move on to the next tutorial? Okay, let's get to it. Tutorial 8, hyperparameter tuning. So this tutorial has some large blocks of code. They also take a long time to run. So we're not going to worry about typing them out. We are simply just going to walk through the notebook as is and discuss it. So we've talked about hyperparameters before. The simplest example of one is in k-nearest neighbors, the n number of neighbors. And the hyperparameters of a machine learning algorithm control various aspects of it, which usually have an impact on its flexibility. So greater flexibility can be a good thing because it allows for the model to react to details of the data more flexibly. However, if you have too much model flexibility, you can also lead to overfitting, where the model is far too sensitive to the noise, which doesn't really have much information into it. So sometimes it's preferable to actually restrict the flexibility of the model to reduce this overfitting. And the trade-off between flexibility while at the same time avoiding overfitting is really what's encapsulated in the variance bias trade-off. So in your homework, you're going to be making predictions on student loan prepayments, and you're going to be asked to select optimal hyperparameters for decision trees and random forests. And the purpose of this tutorial is to provide you some example code to help you get started with your assignment. So as usual, we import what we need. We are going to import the time module because we'll want to measure run times for these things, because I do think that's an important factor. Let's say you have a model that has slightly better performance but takes 10 times as long to run. It's probably just better to use the faster model. And we're going to do some plotting with Seaborne and Matplotlib. So we read in our data. It's the usual data set. We can look at the columns. We've already talked about those. We can again organize our features and our labels, get those into a nice format. So let's talk about K-fold, which is really what's going to help us in doing the cross-validation by hand, which we'll need to do for expected value of UPV. And again, writing cross-validation from code from scratch involves writing a bunch of for loops and really yields very little insight. It's just implementation details. So sklearn is great because it has all these convenience functions. And one of these convenient functions is called K-fold, which produces arrays of indices that define a K-fold cross-validation. So let's see how exactly this works. So we'll import K-fold. Ooh, my connection is unstable. Let me just give it a second. Okay, so we import K-fold, and then we say K-fold n splits 2, shuffle true, random state equals 0, and stick that into a variable. And then we can use a for loop to inspect these indices. So in the first iteration, the train set is this, and the test set is this. And then when for the next iteration, the train test is going to be what it was, the test set, and the test set is going to be what the train set was up here. And that's because we have a twofold cross-validation, which is splitting everything into two parts. So your little Google research challenge is look up stratified K-fold and describe what the difference is between it and K-fold. So I'll give you guys a few minutes to work on that. Okay, we can discuss this a little bit. So what stratified K-fold does is it preserves the proportion of all the classes, all the label classes in the various cross-validation sets, which can be nice if you want. I didn't see a need to do that here, and it didn't seem to affect the results. So, so that's k-fold cross-validation. So next we're going to choose an optimal max depth for the decision tree classifier. So what does this mean? So recall that a decision tree algorithm is a process that iteratively partitions the feature space. And for each iteration of the algorithm, a split is made along one particular dimension of the feature space. And the process is repeated until some kind of stopping criteria is met. So the hyperparameters of a decision tree often control various criteria for stopping this iterative splitting process. The more restrictive the stopping criteria, meaning you will stop faster, the less flexible the model will be, the more bias and less variance it will have. And the more lenient the stopping criteria, i.e. you're going to stop slower, it's going to take longer to stop, the more flexible the model is. So the more variance and the lower the bias. So in this section, we're going to demonstrate choosing stopping on optimal max depth value. Basically, we're going to choose an optimal stopping max depth for our student loan data. And we're going to use tenfold cross-validation on F1 score and on expected balance ratio. So we're going to instantiate our model, or we're going to import the constructor. We're going to import F1 score. We're going to use k-fold to create our tenfold cross-validation. And then we're going to, here's a big chunk of code, and we'll just walk through what it does. So we're going to create a list of all the various max depths that we're going to try, 1, 2, all the way up to 25. And we're going to capture average F1 score, average expected balance ratio, and and then the fit time. So for a given max depth, here's what's going to happen. We're going to capture F1 scores, expected balance ratios, and fit time. So we're going to go through our train indices and our test indices. We're going to we're going to organize our features and our labels. We're going to instantiate a model. We're going to fit the model to our training data. We're going to, then we're going to calculate out of sample F1 score and out of sample expected balance ratio. And then we're going to, so we're going to do that for each of the cross-validation folds. And then we're going to calculate averages of each and stick them into the list, their respective lists. So that's what this does. It takes a little bit of time to run. But here's an output stuck in a data frame. So to read this, a max depth of 1 had a F1 score of 0.37, an EV ratio of 1.26, and took I think it was 0.8 seconds to run. And a max depth of 20 had a F1 score of 0.46, an expected value ratio of just less than 1, and a fit time of 13.1 seconds. So if we graph all the F1 scores, we see that we get a maximum of around 10, at around max depth of 10. And for expected balance ratio, I would say anything after 5 is pretty close to 1. Some go lower, some go higher. It's clearly, if you go too low, you seem to be overestimating. And then fit times seem to be linear in terms of max depth. All right, so based on these, so your discussion question is, based on what you see here, which which max depth would you choose? All right, so looking at this, I would choose something in the 7 to 10 range. I would say things kind of even out after 5, 7 here in terms of being close to 1. And, things seem to max out around 10, and I prefer to go with something that has a shorter runtime. So that would be my suggestion, or that's the way I would proceed. And basically, you're going to repeat this exercise, but for a couple of different hyperparameters. And that's going to be your assignment. It's going to be a longer assignment. I'm going to give you guys 2 weeks to do it. And again, I will post the assignment on Friday. I'll also email you individually to let you know what your parameters are, hyperparameters are. All right, are there any questions? Okay, let's move on to the next tutorial. It's going to be a short one. It's basically going over the Datareader function in Pandas Datareader, which is a convenient way of pulling data from various free internet sources. And we're going to use that next week when we start talking about volatility estimation and forecasting. So let's open up Datareader. Oh, geez. Okay. Well, we can just, I don't have I guess it's all filled in here. So that's not what I intended. But in any case, it's not that complex. So typing it all out isn't all that useful. So we'll just talk it through. So Pandas Data Reader is a convenient way to download a variety of online data sources such as Yahoo Finance, Quandl, and Fred Data. And again, my graphs don't have particularly good titles because I was feeling lazy, but you guys don't get to be lazy. So any graphs that you put into your assignments should have proper labeling so the grader knows, so that Zora knows what you guys are doing. So we'll import the usual packages. This new one is Pandas Data Reader as PDR. And then we're going to do some plotting with Seaborne and NumPy. So to grab data from Yahoo, okay, so let's just talk about what we're doing here. Oh, you know what? I think this was a kind of we were just looking at data around coronavirus time. And I think that was the point of it. Because because coronavirus was going down right as this class started last year. And so I thought, let's take a step back and just look at some data and kind of get a sense for it. So I think that's the context for this tutorial. I thought it was a different one. But that's okay. This one's a little bit more interesting anyway. So we can grab data from Yahoo Finance using this get data Yahoo. And one thing that we noticed is that implied volatilities right around coronavirus were about the same at the same levels as the 2008 financial crisis, but the overall price decline was much faster for the pandemic. And it was super fast going down, and it was super fast coming up. It was very, very abrupt. And it was the fastest such decline ever. So yeah, when you grab, so I grabbed SPY data and VIX data from Yahoo, and when you grab multiple symbols, it comes back as panel data, which is kind of annoying. I would never use it that way. So this is the way that you can grab the data that you want and put it in the format that you want it. So we'll just grab the adjusted close prices from this, change the column names, and put a trade date column in there. So here we're calculating daily returns, realized volatility, and plotting them. So here's just the prices. Here's daily returns. And the cool thing about this is if you just plot daily returns as a line graph, you can kind of easily see high volatility and low volatility periods. And you can see this right here. Okay, and this is 08, this is pandemic. And then we have a trailing, I think, 20-day realized volatility. And here's VIX, which spiked up to same levels as 2008. So again, grabbing some Yahoo Finance data and just seeing how I was interested in REITs last year because I was leading a research project for the Carlson School of Business Masters in Science Finance program, a similar program to the MFM, more businessy, less quant, but the project that we had involved REIT, so I wanted to get kind of familiar with that space. And so we just found that REITs fared worse in equities, and also that small cap got hit bigger than big cap, IWM versus SPY, which is typical of a sell-off. And REITs are just going to perform poorly, I think, in a more long-term sense as well, because there's such downward pressure on commercial real estate needs because everyone's working from home. And I think the general consensus is this is going to be the new norm, more of a hybrid model for the foreseeable future. So another thing that typically happens during times of stress is a flight to quality, which means people rush into U.S. Treasuries, basically, which is going to make the 10-year Treasury rate plummet. And so we can grab data from Fred to take a look at this. And I feel like every day or every week there was a new all-time low in the 10-year Treasury rate. What is the 10-year Treasury now? 10-year. Okay, 162. Oh, okay. It dipped down into 50 basis point range. So crazy. Okay, so this is really just a kind of overview of how to use Pandas data reader for various things. And I don't remember if we actually need this for subsequent analysis or if I just did this because I gave them an assignment last year to just explore what was going on in the markets because of the pandemic, because I think it was on everyone's mind. So that was pretty much it. Yeah, feel free to look through this some more. I have to admit I didn't read over this before this lecture, so I'm forgetting what exactly was in here. Okay. Right, so you can actually grab Quandl data as well, but you need to create your own account. And so that's why I just saved everything in here. So a point that he makes here is that, or the point that I was making here is that one of the reasons why there was such a quick sell-off is because valuations were extremely high, even by historical standards. And so when people got freaked out, the crash came a little bit harder, but it spiked right back up for a variety of reasons. So any questions on Pandas data reader? And again, if you need to look at this, you can use that as an example. All right, so the next section is about volatility forecasting, and that's a whole other topic. So I'm just going to let you guys out early today, and I'll stick around for questions.